Here we are in section 22 of the SAT Math Manual, where we are going to talk about three-dimensional or solid geometry. These questions are extremely rare on the test. You might go an entire test or two without seeing any of these. At most, you're going to see one per test. We're talking about prisms, cubes, cylinders, and so on. Really good news here is that the formulas for most, if not all, of the 3D solids you're going to see on the test are given to you at the beginning of each math section. So at the beginning of section 3 and at the beginning of section 4, you're going to get a page that gives you a bunch of formulas, and on that page you are going to have the formula for a rectangular prism, a right circular cylinder, a sphere, a right circular cone, and a square pyramid. So you will not need to memorize these formulas. I will say if you are going for an extremely high math score, it is probably, for the sake of speed and confidence, a good idea to memorize these formulas so that you don't need to flip back to the beginning of the section. But certainly if you feel like trying to shove any more information into your head could do damage to your brain, then just go ahead and use the info pages at the beginning of the sections to get these formulas. In terms of these formulas, just want to make one point when it comes to a few of these shapes. The sphere is an exception, but when it comes to volume formulas for various solids, you should know that in most cases you can think of the formulas as the area of the base of the solid times the height. So for instance, in the right rectangular prism, you will notice that LW, length times width, that is the area of this rectangular base of the rectangular prism. So if you take L times W times H, that is exactly the same as taking the area of the base times the height. The same thing is true in the right circular cylinder. I'm going to sort of complete the base circle here. That's kind of ugly. I'm going to redo that. I'm going to complete the base circle here. So that is a circular base of this right circular cylinder, and of course the area of a circle is pi r squared. So pi r squared h can also be thought of as base times height. Again, over here, the length times the width is the area of the base. I'm using a capitalized B here to designate the area of the base, not to be confused with the lowercase b that we use to represent the length of the base of a polygon, the length of the base of a polygon. For instance, when we're calculating the area of a triangle, aka 1/2 BH. So I'm using a capitalized B here to notate that area of the base. So with the right circular cylinder, I could take the area of the base, that pi r squared, multiply it by the height, and I would have my volume. And again, that is true of a lot of these solids. We can take the area of the base, multiply by the height. Of course, with the right circular cone and with the square pyramid, there are some fractions we also need to multiply by. They happen to be 1/3 in both cases, but it is important to note that you can determine the volume for a 3D solid by having the area of the base. You don't necessarily need the length and the width individually. You don't necessarily need the radius individually. You can determine the volume of the solid with the area of the base. Let's do a couple of examples so we can see what these questions might look like. I would probably pause the video here and try these examples on your own before watching me work through them. They should not be all that difficult. A box in the shape of a right rectangular prism has a volume of 120 cubic inches if the dimensions of the box are 8 inches by 6 inches by 8 inches. We need the value of h. All right, pretty straightforward question here. What we're going to do is we are going to write the formula, length times width times height. I am going to set that equal to what that formula equals. Remember, length times width times height is the volume of a box or a rectangular prism. That formula again is given on the test. And now I'm just going to start substituting. I have got the 8, the 6, and the h. It doesn't really matter where I put the 8 and the 6, but I'll put the 8 as the length, the 6 as the width, and the h as the height. And that all equals 120. 8 times 6. I can use my calculator here. I'm going to do 8 times 6 in my head, even though most of the time I encourage you to use the calculator, whether you think you know something in your head or not. The 48s there will cancel. I get h equals 120 divided by 48. I could start reducing that on my own, but I'm going to go ahead and type that in the calculator. 120 divided by 48. And I get 2.5. So my height, is that what they were asking me? Yes, it is. For my h, my height is 2.5. Keep in mind, I could answer, if this were, for instance, a grid-in, I could answer as 2.5 or 5 halves there, or even 10 over 4 if I wanted to be crazy. Example 2, again, probably best to pause the video and try this on your own. In a food packaging facility, machine A drops a pre-measured amount of chopped vegetables into a cylindrical jar with a height of 10.5 centimeters. Sounds very appetizing. Machine B then fills the jar to the top with 140 cubic centimeters of broth before machine C seals the jar. If the area of the circular base of the jar is 60 square centimeters, what is the volume in cubic centimeters of the chopped vegetables dropped into the jar by machine A? Okay, bunch of stuff going on here. Let's see, where do we want to start? I think the way that we're going to do this is we're going to find the total volume of the jar, and then we're going to subtract out the volume of the broth, and then that will give us the volume of the chopped vegetables. So let's go ahead and write our formula as we should do. Pi r squared h. We know that the area of the base, this is one of those cases where we do not need the radius. We know that the area of the base is 60 square centimeters. So I'm going to plug in 60 for pi r squared. That is the area of the circular base. I'm going to multiply that 60 by 10.5. I'm going to put those in parentheses because I don't want that multiplication dot to get confused with the decimal point. So I am going to multiply 60 by 10.5. I'm going to get 630. So my total volume here is 630. Make sure I write my units, cubic centimeters. I should have written my units there and there as well. This would have been centimeters squared. This would have been centimeters. So I get 630 cubic centimeters total. And then, of course, as I said a moment ago, we just need to take away the volume of the broth that was added, which will leave us with the volume of the chopped vegetables. So what is this going to be? Again, I'm going to use the calculator here. I don't want to waste brain power on that calculation. 630 minus 140 should be 490. 490. There we go. 490 cubic centimeters. Let's make sure that's what they were asking. So again, this was the total. This was the broth, and the broth plus the chopped vegetables should equal the total. So 140 and 490 equals 630. So there we go. Yes, that 490 is the volume of the chopped vegetables. More on prisms. So a high percentage of the very few 3D geometry questions that you will see may deal with prisms. Mostly these two prisms on the left. It's not all that common. Very small possibility you'll deal with a pentagonal prism or a hexagonal prism. So all prisms have the same components. They're going to have, I'm going to highlight this here, two identical and parallel polygon bases. And those bases, I'm going to switch colors here, are going to be connected to each other by a series of rectangular faces. So, for instance, in the triangular prism over here on the left, I have a triangular base in the front, I have a triangular base in the back, and then I have a series of rectangles connecting each of the corresponding sides. So like this side to this side is connected by this rectangle here that is sort of facing to the right. Same thing with the rectangular prism. I've got a rectangle on the front, a rectangle on the back, and then of course I've got four rectangular faces connecting those rectangles. Over here on the right, we've exploded this hexagonal prism so we can sort of see all the pieces. You can see the hexagon on the front, the hexagon on the back, and then you have 1, 2, 3, 4, 5, 6 rectangular faces connecting the hexagonal bases in the front and the back. And of course, the number of rectangular faces is equal to the number of sides of the polygon. In the triangular prism, triangles have 3 sides, so we need 3 rectangular faces to connect the triangular bases on the front and the back. With the, let's say, hexagonal prism we just saw, hexagons have 6 sides, and therefore we need, again, the 1, 2, 3, 4, 5, 6 rectangular faces connecting the hexagon bases. Prisms are named, very important to know that prisms are named according to the bases. So a triangular prism, a rectangular prism, and it doesn't matter how the prism is oriented. Some students do get confused by this. So some students will see this prism here, and this prism seems to be lying on a rectangular face, right? This, let's call it the, you might even call it the base of this 3D solid, looks like it's one of those rectangles. However, that quote-unquote base is not a base at all. The bases here are the 2 identical parallel triangles on, let's say, the left and the right of the figure. In a moment, we're going to reorient this figure so that it actually rests on one of those triangular bases. But it is important for you to understand that it doesn't matter how the prism is oriented. You've got to look for the 2 polygons that are identical and parallel. And once you find those 2 polygons, you will know what kind of prism you are dealing with. This here is a triangular prism, despite the fact that it seems to be resting on a quote-unquote base that is a rectangle. The general formula for prism volume, and we saw this a moment ago when I said that we could always determine volumes of 3-dimensional solids using the area of the base, and that's exactly what we're going to do with prisms. We are going to take the area of the base, and we are going to multiply the area of the base by what we can call either the length or the height, and those are the same thing. Those are synonymous here. Length and height simply mean the distance between the 2 polygon bases. You could also call that the length of the rectangular face. So let's take a look. These 2 triangular prisms we've already seen, this one here and this one here. What we're going to do is we're going to tip these or reorient these so that they rest on one of their actual bases. So I'm going to take this triangular prism, I'm sort of going to, I don't know, tip it forward, and now we can see that we are resting on the triangular base here. We're now resting on that, and the height of this prism is the length of one of those rectangular faces. So there's one of the rectangular faces over here on the right, the shaded ones on the back, and the length of that rectangular face is also our height. We are going to now reorient this triangular prism that we saw a moment ago. I'm just sort of like tip it so that this base here, this triangular base here, is the actual base now. It's actually what the prism is lying on or resting on. And again, we can see that the length of this rectangular face is now the height of the prism when the prism is resting on its actual base. Let's try an example. I would definitely pause the video and try this on your own. Hopefully this should not be too difficult. Volume of a prism, example 3. The right triangular prism above has volume 60 cubic centimeters. What is the value of K? So keep in mind that K, what is that? That is the height or the length, right? It is the length of the rectangular face. It is also the distance between the 2 triangular bases, this one on the left, this one on the right. So that K is going to be our H or our L. And then, of course, in terms of the prism formula, so we know this guy here is going to be the K, right? The length is K. And then the area of the base here is going to be the area of this triangle. So let's write this down here, base times K, and of course the area of the base here is the area of the triangle, which we can find by doing 1/2 of 2 times 3 or 3 times 2. It doesn't matter which of these two values is the base and the height of that triangle. 1/2 2 times 3, or 1/2 3 times 2 times that k, and we know that our volume here is going to be 60. So now we've just got a simple basic equation to solve. 1/2 times 2, the 2's will cancel, cannot use the calculator here. We get 3 times k equals 60. We divide by 3, we get k equals 20. Let's make sure that's what they were asking it is, and we know that our length or our height or our k value is 20. In terms of the width and the area of those rectangular faces that connect the bases of the prism, those parameters are generally not going to be relevant when we calculate volume. Of course, when we start to deal with surface area, which we're going to do in a moment, the area of those rectangular faces or the width of them will become important. So let's talk about surface area, where those things might become important. Surface area questions do not show up often. If they do, you are almost certainly just going to need to deal with the surface area of a rectangular prism, maybe of a triangular prism, but again, pentagonal, hexagonal prisms don't tend to show up often. There is a formula for the surface area of a box, but we do not suggest memorizing that formula. We would rather you just know how to construct the formula and then use that construction process in solving these questions. That construction process is laid out basically here. What you're going to do is you're going to find the area of the visible faces, the faces that are visible in the given figure or in a drawing that you've made. You're going to add those areas together, and then you're just going to double the result, because and then, by the way, here, maybe I should draw this. By the way, you should know how to draw a rectangular prism. There are multiple ways to do this. This is the way that I do it. However, you should know that you can also draw one rectangle, draw another rectangle that sort of overlaps the first rectangle in the upper right, or even you could do it over here as well. That would be perfectly fine. Little bit of overlap, and then you just connect the corresponding vertices. And now you've got a rectangular solid drawn. Again, I tend to do it like this. I draw my rectangle. I draw the sort of depth, the depths of the rectangular prism, and then start connecting all of the open ends. So in terms of what is detailed here, you have 3 visible faces. You have the front, you have the top, you have the right. And remember, for each of these faces, you've got another one. The front has the back, the top has the bottom, the right has the left, that are identical to the 3 visible faces, so that if you add the top, the front, and the right to each other, and then multiply that sum by 2, you will have the entire surface area. Of course, there is a chance that a question might say that the box is open on top, in which case there is no top face, so you would only have to add in one of those to account for the bottom, but not the top, and so on and so forth. Let's take a look at an example here. Example 4, surface area of a prism. Again, I would pause the video and try this on your own. Rectangular prism has a length of 8 inches, height that is 50% greater than the length, width that is 75% less than the height. Ooh, wow. To the nearest tenth of a square foot, what is the surface area in square feet of the rectangular prism? So notice we do have a unit change here. We're going to have to be a little bit careful about that. We need the surface area in square feet, and I am going to circle the rounding instructions here. Always important to circle the rounding instructions. Tenth of a square foot. So how am I going to do this? Well, first, let me go ahead and draw my rectangular prism. The length is 8 inches. I'm going to write my units. That's going to be the length. The height, I'm going to slash my phrases here. The height is 50% greater than the length. So this height is 12 inches. Now, how can I do that? Multiple ways. One way is that one-step percent increase decrease method, where I take 50% greater and I convert that to 150%. So 100 plus 50 over 100 is 150%. So I know that my height is 150% of my length, which is 8. I can go in my calculator and do this calculation, and I will get 12. By the way, all of this stuff is covered elsewhere in the manual in the percents section and also in the exponential functions section as well. The width, I am going to write this out. The width is 75% less than the height. Well, remember, 75% less than something is 100 minus 75 over 100. That is, what's that going to come out to? That's going to be 25%. So a 75% decrease is the same as saying 25% of a number, and that is 25% of the height. So that is of 12, and again, I can do that in the calculator. It's going to come out to 3, but I'm going to do it in the calculator anyway. So I go alpha F1. I want to enter this as a nice, neat fraction. So 25 over 100. I am going to multiply that by 12, and indeed I get 3 inches. So that is this dimension here. Now, one of the things I do like to do when I am calculating surface area is I transfer all of my dimensions. So I'm going to write a 3 up here, an 8 up here, a 3 over here, an 8 here, a 12 here, and a 12 here, just so that I know what each of those edges is, so that I don't make any careless mistake about, I don't know, putting in an 8 where there should be a 12 or a 3 or something like that. And now what I'm going to do is I'm going to find the surface area of the visible faces, the front, which is visible to me. I am going to multiply 12 by 8 and get 96. 12 times 8 is 96. I'm going to write that area right there on that face so that it's very clear. The 12 times the 3 is 36. I could check that in my calculator if I needed to. And up top, I've got 8 times 3, which is 24. So to get the total surface area, I need to double each of those. 2 times 96, 2 times 24, 2 times 36, add them all together, but that's all the same as 2 times 96 plus 36 plus 24. I'm going to do that in the calculator. I don't want to waste brain power on that. So 2 parentheses 96 plus 36 plus 24, and I'm going to hit enter, and I get 312. That is in square inches. Now we need to go to square feet here. This is very tricky for those of you that have done the ratios, proportions, units section. You will recall that what we need to do here is we need to square the conversion factor. So I need inches to cancel, but this is inches squared. I'm putting inches here. I'm going to put feet here. In order to get to square feet and square inches so that those square inches cancel, I'm going to have to square this conversion factor of 1 to 12. So what ends up happening here is I'm actually not dividing by 12 itself. I am dividing by 144. But I'm going to let the calculator do the work here. I'm going to do 312 times parentheses alpha F1, enter 1 over 12, end parentheses, and I'm going to square that conversion factor, and what I get is 13 over 6, but I do need to round here. They instruct me to round. So what I'm going to do is I'm going to convert that 13 over 6. There are multiple ways that I can convert a fraction to a decimal in my calculator. One of those ways is by doing alpha F1. Again, if you have the TI-84, this is where you can do it, and I'm going to go to number 4. And I'm going to convert that. I can also access that conversion in the math menu. I can go math and number 2, which is the 2 decimal conversion, convert to decimal, and hit enter. And again, I get 2.16 blah, 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 blah feet squared. They want me to round to the nearest tenth. That 6 in the hundredths position tells me that I need to round this 1 in the tenths position to 2. And now that should be it. Surface area, square feet, and yes, 2.2 feet squared. That is it for number 4. Let's try one more. In this case, we're going to need to go back to what we learned in quadratics. I would pause the video, try this question on your own. So in number 14, we've got the width of a rectangular box is 2 centimeters less than its length. The height of the box is 8 centimeters. Which of the following functions represents the surface area in square centimeters of the box with side length x? All right, so again, a lot of stuff going on here. I'm going to do this two ways. I'm going to do it algebraically, and then I'll actually do it using VITA, using a throwing in numbers technique, which some of you have learned by this point. Most of you have probably learned by this point. In terms of surface area, I'm going to draw my box. That's the first thing that I'm going to do. And I'm going to start labeling these dimensions. So the width and the length I don't actually know yet, so let me hold off on those. They do tell me that the height is 8, so these are all 8. They tell me down here that the length is x, so I am going to write that. So my length is x. And then they say that the width is 2 centimeters less than the length. So that means that this width here is simply going to be x minus 2. And that means this here is x minus 2, and this here is x minus 2. And now I think I am sort of off to the races here. The front face will have an area of 8x. The top face will have an area of x times x minus 2, which is going to equal x squared minus 2x. I am just distributing that x out there, so that's x squared minus 2x. And then over here on the right, that is, this right face is 8 times x minus 2. Again, let me write that out so I don't make any careless mistakes. That 8x minus 16. So this is 8x minus 16. And now remember what I do is I add those all up. 8x, that's the front face, plus x squared minus 2x, that's the top face, plus 8x minus 16, that's the right face, and I'm going to multiply all of that by 2. Let me start cleaning this up. So 8x is 16x minus 2x, so that's going to be 14x. I'm going to put that in the middle. I still have my x squared there, nothing to combine with that x squared, and then I have minus 16. I'm multiplying by 2. That's 2x squared plus 2x squared, 28x, and then minus 32. That should be my surface area. 2x squared plus 28x, 2x squared, 28x, 32. There's my answer, B. That is the surface area. That's what they were asking. Now listen, if that algebra got complicated for you or intimidating for you, there is, so this is the algebraic method. There is the TIN, more specifically the VITA approach. We know we can use VITA here because we have variables in the answers. This is a no calculator question, which means that the VITA, if you do not use a nice small number, the VITA can get a little bit unwieldy. But if we do something like this, so let's list our variables. We have x, which is the length. We have the width, and then we have the height. So we've listed our variables. I'm going to make x equal to 3, which means my width is going to be 2 centimeters less than that length x. So that's going to be 1. I generally don't want to use 1 on VITA, but because I am on a no calculator section here, I'm going to let it ride with the 1. I'm going to see what happens. Should work out okay, and if it doesn't, we'll fix it. And then the height, of course, is 8. So again, I'm going to draw my box. I'm going to label all those heights. I'm going to label all of those lengths. I'm going to label all those widths. So the front face is 24. That's 8 times 3. And the top face is 3. And the right face is 8. So that's pretty easy. So now what I do is I add the 24, the 3, and the 8, and I'm going to multiply that sum by 2 to account for the non-visible faces. 24 plus 3 is 27 plus 8 is 35. 2 times 35 is 70. Remember, in VITA, we want to box the numeric result that we get. And now when I go to the answer choices, I'm going to try to find 70. So answer choice A is going to be, remember our x was 3, so that is 9 plus, what is 14 times 3? You know what, that one I'm going to write out. 2 and carry the 1, 3, so that's 42. 9 plus 42 minus 16. I don't even need to calculate that. I know it's not going to get me up to 70 because 9 plus 42 is 50 something, and then I'm going down by subtracting the 16. So A is not going to work. B is going to be 2 times 9, right? X squared is 9, so that's 18 plus, this is 28 times 3. I am going to do that here. That's 4, 24, carry the 2. This is 84. This one's looking fairly good, minus 32. So 84 minus 32, let me do that first. That's going to be 52 plus 18. That sounds good. 52 plus 18 sounds like it's going to get me right around 70. Answer choice C. 16 plus 2 times 3 is 6 minus 9. That's not going to be nearly big enough. It's not going to get me even close. And then answer choice D. 32 plus 4 times 3 is 12 minus, we already had a 2x squared up here, so that was 18. Again, that's not going to get me close enough. This is going to get me into the 40s, and then I'm going down from there, so I'm done. So again, if the algebra was intimidating here, it's not a big deal. You can use the VITA. Yes, the VITA does require you to do some arithmetic that might seem a little bit intimidating, but generally intimidating arithmetic is better than intimidating algebra for some, maybe most students. So those are the two ways that we could have handled number 14. Obviously, the most important thing here is just to understand how to construct, how to derive the surface area of a rectangular solid. That is it for rectangular solids. Again, you'll need to know a little bit about prisms and how to name them. You should know that the formulas are given to you at the beginning of the section as well. So naming prisms, volumes for prisms, how to find surface areas of generally just rectangular prisms or boxes. And if you know all that stuff, you should be fine.